Hi all, this is Dr. K.G. Shanti, Professor, EC Department, R.M.K. College of Engineering and Technology. In this particular video, we are going to study about wave equations and their solution. Now, what are electromagnetic waves? If a physical phenomenon that occurs at one place at a given time is reproduced at other places at later times, then this time delay is proportional to the space separation from the first location. Then this group of phenomena constitute a wave. Right? Waves are means of transporting energy or information. A wave carries energy from one place to another and it is a function of both time and space. Typical examples of electromagnetic waves include radio waves, TV signals, radar beams, and light rays. All forms of electromagnetic energy share three fundamental characteristics. They all travel with very high velocity, they assume all the properties of waves, they radiate outward from a source. Maxwell was the person who predicted the existence of electromagnetic waves and he established Maxwell's equations. The same EM waves were investigated by Heinstein-Rich Hertz. Hertz conducted several experiments on EM waves and he succeeded in generating and detecting radio waves. These radio waves are called as Hertzian waves. Applications of EM waves. They have a wide variety of applications in all type of communication like television, satellite, wireless, cellular and mobile communications. EM waves are also used in radiation therapy and microwave ovens. They are also used in all types of radars like Doppler radar, airport surveillance radar, weather forecasting radar, remote sensing radar. The major goal is to solve Maxwell's equations and describe EM wave motion in following media. We have four types of media. Based on conductivity, we define what is the media. For free space, we have sigma is equal to 0, permittivity is epsilon naught, and mu is mu naught. And we have what is called as lossless dielectrics. We have lossy dielectrics, and we have a good conductor. Lossless dielectrics is one where sigma is equal to 0, whereas lossy dielectrics is one where sigma is not equal to 0, which means that it offers some amount of conductivity. For a good conductor, that is sigma is going to be infinity. And here for lossy dielectric, lossless dielectric and good conductor, we have mu r value and epsilon value depending on the medium. And we are going to see what is called as a homogeneous medium. A homogeneous medium is one where sigma, epsilon and mu are constants throughout the medium. And the medium is isotropic if epsilon is constant and D and E have same direction everywhere. Now let's study about wave propagation in free space. When I say free space, it's source free wave equations. Now as I told you earlier, for free space, sigma is equal to 0. When I say sigma is equal to 0, conduction current density J is equal to sigma E, even this becomes 0. And for free space, the medium is sourceless, which means that the charge density rho V is 0. Now these two conditions are going to be applied to the Maxwell's equations. Right? Now the Maxwell's equations for free space are going to be like this. We have del cross H is equal to dou D by dou T, which is equal to epsilon naught dou E by dou T. Here actually the equation would have been del cross H is equal to J plus dou D by dou T. But here since J is equal to 0, you get this equation. Now del cross E is equal to minus dou B by dou T, which is equal to minus mu naught into dou H by dou T. And the third equation, del dot D is equal to rho V actually, but for free space, rho V is 0 and hence we get del dot D is equal to 0. And the fourth equation is del dot B is equal to 0. Now let's look into wave equation for electric field. Right now we have a small derivation. Del cross H is equal to dou D by dou T, which is equal to epsilon naught into dou E by dou T. Right now what I am doing is I am going to differentiate the above expression with respect to time. Right, so dou by dou T del cross H is equal to epsilon naught into dou square E by dou T square. Right, now here we have two operators. The del operator is differentiation with respect to space, while dou by dou T is differentiation with respect to time. Both are independent of each other, so they can be interchanged. So when I interchange it, what will I get? Del cross of dou H by dou T is equal to epsilon naught into dou square E by dou T square. So on the left hand side, I have interchanged the operators dou by dou T and del. Now taking the curl of the equation, right? Now when I take curl of the equation, that is take this second equation, del cross E is equal to minus dou B by dou T, which is equal to minus mu naught into dou H by dou T. When I take curl of this equation, del cross E is equal to del cross of minus mu naught into dou H by dou T. Now we have an vector identity. Del cross E is equal to del into del dot E minus del square E. Right. Now I rearrange the that is look at del dot of del into del dot E minus del square E, which is this part. This part is nothing but equated to right hand side of equation 4, minus del into mu naught into dou H by dou T, or minus mu naught into del cross of dou H by dou T. Now what I am doing is I am going to substitute 3 in 6, which means what will I get? Del dot of that is del into del dot E minus del square E is equal to minus mu naught into, already we have found out del cross of dou H by dou T is nothing but epsilon naught into dou square E by dou T square, which is equal to minus mu naught epsilon naught into dou square E by dou T square. Now from equation del dot D is equal to 0, or del dot epsilon E is equal to 0, or del dot E is equal to 0, since because epsilon naught is not equal to 0. Now we are going to substitute this equation in equation 7. So what I get? Minus del square E is equal to minus mu naught epsilon naught into dou square E by dou T square. In the same way, del square E is equal to, this minus and minus gets cancelled. You have mu naught epsilon naught into dou square E by dou T square. So this is the wave equation for a time varying electric field in free space. In the same way, we have to derive the wave equation for time varying magnetic field in free space conditions. Now wave equation for magnetic field. So we start with del cross E. Del cross E is equal to minus dou B by dou T, which is equal to minus mu naught into dou H by dou T. The same way we have to proceed as we have done for electric field. So differentiating of the above equation with respect to time. Then we interchange the del operator and dou by dou T. So what I have, del cross of dou E by dou T is equal to minus mu naught into dou square H by dou T square. Now take the curl of this equation del cross H. Del cross H is equal to dou D by dou T, which is equal to epsilon naught into dou E by dou T. Now taking curl of this equation, I get del cross H is equal to del cross of epsilon naught into dou E by dou T. Now apply the vector identity. So del cross H is equal to del into del dot H minus del square H. Now what I do, I replace I compare equation 4 and 5, right? So I equate these two equations. So what will I get? Del into del dot H minus del square H is equal to epsilon naught into del cross of dou E by dou T. Right, now what I do, instead of del cross dou E by dou T, I am going to replace minus mu naught into dou square H by dou T square, which I have got in equation 3. So I substitute 3 in 6 and I get this equation. So what I have, del dot B, this is a Gauss law for magnetic field. Del dot B is equal to 0. Del dot mu naught H is equal to 0. Since mu is not equal to 0, we have del dot H is equal to 0. Now I substitute 8 in equation 7. So what I get? Minus del square h is equal to minus mu naught epsilon naught into dou square h by dou t square. Or this minus sign gets cancelled and I have del square h is equal to mu naught epsilon naught into dou square h by dou t square. And this is the wave equation for time varying magnetic field in free space conditions. So the wave equations for electric and magnetic field are del square E minus mu naught epsilon naught into dou square E by dou t square is equal to 0. And del square H minus mu naught epsilon naught into dou square H by dou t square is equal to 0. Or we can, you all know mu naught epsilon naught is nothing but, velocity is nothing but 1 by root of mu naught epsilon naught. So it's 1 by u square. That is where u stands for velocity. U is equal to 1 by root of mu naught epsilon naught. Right? So 1 by u square into dou square E by dou t square is equal to 0. Similarly, here I replace mu naught epsilon naught by velocity. So del square H minus 1 by u square dou square H by dou t square is equal to 0. So the above equations are going to be called as homogeneous vector wave equations, and it is this vector equations, which are used for solving many solutions. Actually, these two equations are the one which describe wave propagation.